Good morning, afternoon, or evening, wherever you are across the world. Today's video, we'll be having a mini lecture on wall slip in emulsion rheology. My name is Chris Sir, and I'll be leading today's discussion. At the outset, I want to thank Powell and Barnes for their work, whom form the theoretical basis for today's discussion. Diving right on in, we're going to discuss a few topics today. First, from our previous lectures, we will review what emulsions are, rotational rheometers and important parts, and what wall slip is. We'll talk about why this is important through the vein of emulsions being part of our everyday lives. We'll talk about the causes of wall slip, the effects of wall slip on both our classical rheometry and oscillatory shear, the indicator and primary tests for wall slip, and some preventative measures to avoid wall slip from occurring. For our review, let's recall that emulsions are one of two subgroups of the dispersant material classification. Dispersants are made of two primary components, the continuous phase, otherwise this is the bulk of our sample, and the dispersed phase, which is the smaller component contained within the larger continuous phase. The two subcategories are suspensions, of which the dispersed phase are solid-like particles, and emulsions, which are dispersed phase are liquid-like droplets. For rotational rheometers, let's recall that there are three main designs: the concentric cylinder, or CCV, the cone and plate, or the parallel plate, each of which with a multitude of customizable spindle options for our use. Let's also recall that these rotational rheometers are used for our oscillatory shear measurements. When we zoom in on our important pieces, we can see down here a depiction of the measuring bob, otherwise called the spindle. Our sample shown here in red, contained within the measuring cylinder, otherwise called our cup. What is wall slip? In a physics sense, what wall slip is, it is a breakdown of the continuous fluid assumption. If we take a look here on the left, we can see a top-down view of our spindle, our emulsion shown here in the blue and red dots, where our red dots represent our dispersed phase, the blue our continuous phase contained within our sample cup. For the continuous fluid assumption to be true, we need an even distribution amongst our dispersed phase droplets within our sample. What occurs in wall slip is more akin to our image here on the right, where our dispersed particles are no longer evenly distributed amongst the sample and are now more concentrated closer to our cup than to our spindle. Thus, we have a gap from our spindle to our dispersed particles. This is found to be between 0.1 and 10 microns in size. That varies quite a bit depending on the sample's characteristics. And when we spin up our sample to test it, we will no longer have any dispersed particles interacting with our spindle, giving us a misrepresentative test, as we are only testing our continuous phase of our sample when wall slip occurs. Now, a valid question is, why would any of this matter to us in our everyday lives? And the reality is that emulsions are a great kept secret simply because everyone already knows about them. They are very much so hidden in plain sight in our everyday lives, both industry and in our own homes. In industry, the petroleum and gas industries are no slouch. They use a variety of oil and water and oil emulsions for all sorts of processes. In our own homes, there are many examples, some of which include our homogenized milk, the toothpaste 4 out of 5 of our dentists recommend, and the cosmetics that we all use. So understanding this affects not only big industry, but our own homes. Now, what actually causes wall slip? There are three major explanations as to the cause of wall slip. First is electrostatic repulsion. This is a repulsion between the spindle charge and the charge of our dispersed particles. Should these charges match, we will find it energetically favorable for our dispersed particles to move away from the spindle, thus creating that gap. Secondly, we can have a density difference. This density difference is between our continuous phase and dispersed particles. Should our dispersed particles be more dense than our continuous phase, as our spindle begins to spin up the sample, our dispersed particles will be more encouraged to move away from the spindle and thus concentrate around the cup, again creating that gap. Finally, steric forces. Depending on the molecular characteristics of our dispersed phase, These particles may attempt to find more space amongst the relatively larger area around the cup compared to that of the spindle. Any one or all three of these can lead to or contribute to wall slip occurring. It may be a case of a single one or all three being a factor. When wall slip occurs, we can see a few different effects. When we look at our classic rheometry data, we have two major things that occur. First is a spike in our shear stress on our classic rheograms of shear stress versus shear rate shown here. This chart shows three different examples of designs, a serrated parallel plate and two cone and plate geometries, each of which experience the sudden driving spike in our shear stress values. We can also see a sudden drop in our viscosity. This is shown on a viscosity versus shear stress curve. Again, with those same three designs, we can see consistent values and then a sudden drop at a particular shear stress value for our viscosities. Not only our classic rheograms are affected, but also our oscillatory shear. When we look at oscillatory shear, we typically want to see a nice linear curve for our elastic modulus G prime and viscous modulus G double prime, such as shown here for our serrated parallel plates. When wall slip occurs, we see more erratic behaviors, such as the viscous modulus for the serrated plates, as well as erratic behaviors for both of our cone and plate geometries depicted here. What this leads to is inconsistent results as to the elastic and viscous moduli. Additionally, we can see that there are quite significant gap differences between the G prime and G double prime values. Thus, we have an inaccurate representation as to what the solid-like or liquid-like characteristics of our sample could be, giving us a misnomer as to what actual material properties we are working with. Now, should we be concerned about wall slip? There is one very key indicator that is quite often used. First of all, because we know viscosity will always drop when wall slip occurs, should our testing indicate a much lower than expected viscosity, that is the first indicator that we should start checking for wall slip. Unfortunately, we have three great different tests to check for wall slip, giving us a lot of variety. We can go back to our classic rheograms for our shear stress versus shear rate and see that sudden spike in shear stress. That is an indicator of wall slip. We can also look at our viscosity versus shear stress curves. And again, we can see that sudden drop in viscosity on these curves, again, showing us wall slip. And finally, a great tool that we have is we can, as done in PAL's work, use varied geometries and setups to test for different results. We can see here that one of our cone and plate geometries is showing significantly different results than our other geometries. This indicates that wall slip is happening in one or multiple of our tests for this sample. If we're worried about wall slip happening at all, or have detected it and want to avoid it in our subsequent tests, the main thing we want to do is prevent this from occurring. We can mathematically work out wall slip, but this is quite experimentally and analytically rigorous. Our best option is prevention above all. We can do this with two primary methods. First, ensuring we have an ideal particle size to gap height ratio. For example, in cone and plate geometries, we want to ensure that our maximum particle size is no more than 1/10 the gap height in our setup. We can also play with the spindle designs, working with something like this, where we had a serrated parallel plate with additional rivets to give more surface area and traction for our sample to hang on to. We can also use porous spindle designs as a second option to give that additional traction. Now that we have all of this knowledge, hopefully we can make some beautiful rheographic data, because that will make Dr. Sanders a very happy man. And we've all seen what happens when there's very poor rheology data in the literature. It makes for a not happy Sanders. So today we reviewed what emulsions are, important parts of rotational rheometers, and what wall slip is. We talked about why this matters, because they're hidden in plain sight in our everyday lives. We talked about the causes of wall slip, the effects of wall slip on both our classical and oscillatory shear measurements, our key indicator and primary tests, and some preventative measures. Thank you again to Pal and to Barnes, our image credits, and you, the viewer, for joining us today. Farewell.